I'm going to start with what seems like a silly thing to do, but don't miss the surprise at the end, okay? What I'm going to do is imagine that I'm in the world of normal complex numbers and I'm going to remember that to the power of I theta is cosine of theta plus I sine of theta. You know, the old school Euler identity. Let's assume that you either believe this or know it, and for whatever reason someone wants me to tell you how to deduce this. Well, I can do it, but let's assume that we know this and let's imagine that we have a complex number ze equals ax plus y. And we're going to do this innocent multiplication. We're going to put cosine of theta plus I sine of theta multiplied by x plus I. So we're going to go to the real part x cosine and then I is minus 1 and we have I times sine and then the factors that multiply I. Let's put x times sine for example and then we'll have y times cosine. And if we call this x prime and this y prime, it turns out that we can put that in matrix terms like this. Cosine of theta minus sine of theta, cosine of theta. Acting or multiplying it gives us x prime and y prime. You know, this times this plus this times this is precisely x prime and this times this is I prime. In other words, this guy is describing a rotation. You probably already know this, right? So let's get a little more to the point and say, hey, but why might this be happening? Is this describing a rotation or whatever? The key lies in the fact that this object or this number, this imaginary unit squared gives minus 1. This is the key to why all this works. And let's see it with a very easy example. Let's imagine that we invent a matrix, an innocent matrix, for example, this one. And this matrix squared is minus 1, 0 to 1. This matrix squared gives, minus the identity, which I'm going to put with a 1 but it's already understood that it's the identity, simply to write less. So, we ask ourselves if there is a kind of Euler identity, but adjusted with this new object which is matrix A, that is to say, we ask ourselves if you raised to theta by a instead of I, if this is going to give cosine of theta plus sine of theta. That's the question we ask ourselves. Well, you know that the exponential of whatever is here can be written as 1 plus this squared divided by 2 factorial, this to 3/3 factorial and so on to infinity. So, of course, if a squared is minus 1, it means that a cubed, which is a squared a, since a squared is minus 1, then a, or for example that a to the power of 4 will be a to the power of 2 asterisk a to the power of 2 1 1 and so on. In other words, in the end all these powers either give more or less are 1 or minus 1. So if we group the whole thing together we say, okay, let's put the 1. A squared is minus 1, therefore it will be t squared, 2 factorial, a to the power of 4 is 1, therefore, plus t to the power of 4 has been 4 factorial and minus, plus or minus, etc. All this is going to work on one side, and for the odd terms we can factor out the common a. Why? Because a cubed equals a and therefore we can put a minus and t cubed factorial in the 5. Well, 5 will be to the 4th power a. A to the 4th power is 1. Therefore 1 asterisk a is 8. In other words, the term 5 will be plus theta to the 5/5 factorial blah blah blah. And as you can imagine, this is the Taylor series expansion of the cosine of theta and this is the Taylor series expansion of the sine of theta. Therefore, effectively, we remove the question mark and say, this is true, which is the milk inverse. And even more interesting is when we put this in matrix form, because let's not forget that there is an identity here. Therefore, in reality, instead of putting cosine, what we should put is cosine o cosine, because I insist that there is an identity here. And then it's actually minus 1, 1, which multiplied by sine will be minus sine, sine, and therefore, adding this together, it turns out to be the same thing. These are two ways of expressing the same concept, which is a rotation. But let's go a little further. Let's see what a rotation complies with. Okay, in the first case, when we had e to the power of theta, z, which gave us ex cosine I sine plus ih, x sine plus I cosine. What does this new, complex equation that we can call z prime, for example, comply with? It complies with the following. If now I do z prime conjugate by z prime, it turns out that we're going to see that it's going to give exactly the same as z conjugate by z. That is, that with or without primes. This thing is the same. Let's see what it is. Let's start with this first. What is the asterisk times z? Well, z asterisk times z played by z, which is xi multiplied by x plus I, and this is x squared plus y squared, and then the crossed terms cancel out. Therefore, this is basically the modulus of the complex number squared. Very good. Let's calculate the modulus of the complex number now, but first, knowing this information, we're going to go straight and say, okay, so this guy is going to give this squared plus this squared. Let's see, in case you're wondering if I'm going too fast. In other words, if I have a complex number 2 plus 3i, and I wonder what the modulus squared is, you know that this is 2 to the power of 2 plus 3 to the power of 2. That is, taking the real part squared and the imaginary part squared. Well, this is what I'm doing. And I'm doing that because I've realized that z asterisk times z turns out to be okay. So if we do this will be x squared times cosine squared plus y squared asterisk sine squared minus 2 times the first times the second. And here more of the same, the square of the first plus the square of the second plus 2 times the first times the second. And then this is crossed out, and notice that I can factor out x squared and I get cosine squared plus sine squared, which is 1. And then if I factor out y squared I get sine squared plus cosine squared, which is also 1. In other words, it's exactly the same as this. Therefore, it's effectively proven. In other words, this is what's called an invariant. Therefore, what we're saying is that after this transformation, which is going from a z to a z prime, it turns out that what remains invariant is the squared module which remains invariant. This is not very surprising because you already know that in a rotation, if we have a point here and we rotate it through a certain angle, then this distance, which is the module, remains invariant. In other words, there's not much to say up to this point, right? In other words, this is normal in principle, okay? Well, and the same would happen with matrices, believe me. And on the other hand, we also know, as we just saw, that if a squared is minus 1, then e will have to be raised to theta. This turns out to be a matrix that acting on xi gives us x prime y prime. And this is a rotation, which is what we just saw, right? Because this, remember, is cosine of theta plus a sine of theta. Very well, so let's play a little with. We're going to imagine the game now, a typical game that we might ask ourselves, which is, hey, if instead of squared being minus 1, if I invent a matrix that squared gives 1, then what happens? Well, let's see. Let's put another parameter here. Let's put, for example, eta. Eta is a real number. Okay, well, let's see what this would be. Well, we would have the same operation, etc., and we would have the following. Since b squared, I already have it here, since b squared ad in this game we have said that it is the identity. Well, we have 1 plus this which is the entity, therefore, eta squared given 2. To the fourth power, it will be b squared asterisk b squared, therefore, it will be identity by identity, that is, what I wanted to say. Well, we would have this, that is, we would have a lot of terms proportional to the identity, and then we would have the terms that accompany b, which would be a to b squared is already put here, but b cubed, which is b squared asterisk b, since b squared ad is 1, well, this would give b, therefore, to the cube it would give b, so we would have it around here, and you can imagine that the odd terms, well, the same thing is going to happen. And this, as we have said several times in the videos of the courses that I have been doing, this turns out to be the Taylor series development of the hyperbolic cosine of eta, and this the series development of the hyperbolic sine of eta. Therefore, it turns out that if the matrix instead of being squared 1 is 1, then we have to get a hyperbolic cosine plus this matrix by this other matrix.
Perfect. And we ask ourselves the last question of this video. I wanted it to be short and it is getting a little longer. Indeed, it is getting a little longer. We ask ourselves the question if before, what was invariant was this. Before, invariant, what is it? Is there an invariant here? Well, let's see. Let's remember that here if nothing is written it means that there is an identity, right? And we are talking about a space. In other words, B is a matrix and it can be of any dimension, but let's make it easy. And it's a two-dimensional matrix, that is, 4 little numbers in matrix form, okay? Therefore, if we multiply this matrix by a pair of numbers, this is equivalent to doing this. So, let's write the matrix. This is the identity. Therefore, there will be a hyperbolic cosine, and then be sure, we have to invent a matrix that is squared by itself. So, man, we could write the identity, but let's write a more fun one, right? Let's go, depending on, well, this would take us to another topic, but depending on which matrix we use for B, we would be talking about one representation or another. But well, let's imagine that the matrix, let's write a cool one. For example, this one that is not the identity so as not to make it so easy. Well, if we do this, you can see that it is the entire identity. So, we would write, as you can see now, we have chosen a representation that is called, well, we would have hyperbolic sign acting on she. Therefore, this would be our transformed she. And if we raise x prime to 0, to try to do something like that, well, what are we going to have? Well, x cosine plus y sine. We're going to raise this to the square, okay? Which is this lady here. And this gives us x squared cosine squared add plus y squared sine squared plus 2 she sine cosine. And if we do the same with the lady squared, which will be x sine plus y cosine squared, we'll have x squared sine squared plus I squared cosine squared plus 2xy sine cosine. So if we add these things together, well, maybe we could do some trickery, but it's kind of weird, right? I mean, if we add, eta doesn't go away. Notice that here, when we do all this stuff, theta isn't anywhere. So that's a good sign because it means that regardless of the angle theta, this is going to stay constant. So what could we do here to make eta go away? Well, I removed it, but you know it's always around, right? Well, it turns out that if I do this by subtracting, look what's going to happen. I can take out the common factor x squared, and as you know, hyperbolic cosine squared minus hyperbolic sine squared of anything of p minus hyperbolic sine squared of p, where p is a real number, this gives 1. Therefore, when subtracting, for now we've lost this. Then here if we subtract we get exactly the opposite of this. Therefore, it actually gives -1. Therefore you would have an I squared add, but a -1 because it's sine squared minus cosine squared, which I insist is the same as this but multiplied by -1. And if we subtract these terms, since they are the same, they cancel each other out. Equally, we have an invariant in the sense that without primes and with primes this is the same and it doesn't depend on this parameter. And you know that this is the relativistic interval. Therefore, this has to be clearly a Lorentz transformation because it keeps invariant this. Let's say, scalar product or this quadratic form or whatever you want to call it, right? I mean, the conclusion of all this stuff, this fairy tale, well, the conclusion is that if you want a rotation, invent a matrix that gives minus the identity, and if you want a Lorentz transformation, invent a matrix that gives the identity.